Welcome back to our series from the Australian Dizziness Clinics. This is video 2, and we're about to take a journey way back in time, to a moment that completely changed the course of our evolutionary history. Today, we are diving deep into what's known as the Gnathostome revolution, and this was a moment that literally rewired the vertebrate brain and body. We're going to find out how something as simple as a jaw forced a total redesign of the inner ear, creating the amazing vestibular system that gives predators, including us, all of our speed and agility. So our story kicks off in the oceans of the Silurian period, over 400 million years ago. And the evolution of jaws, well, that was an absolute game changer. All of a sudden, vertebrates went from being these passive little filter feeders to becoming truly active, deadly predators. And this, of course, kicked off a massive evolutionary arms race, where the only ones who survived were the fastest, the most agile, and the most precise hunters.
But here's the thing. Having this powerful new weapon created a huge, immediate problem. Because, really, what good is a jaw if you can't aim it? These early vertebrates found that their ancient sensory systems were just completely outmatched by this new ability.
So, what exactly was this new problem for our predator? Let's break it down. To really get what changed, we first have to understand the before. And for that, we can look at living jawless fish, like the lamprey. I mean, these guys are an incredible window into our deep past. Their inner ear, their labyrinth, it's basically a living blueprint of the ancestral model. And if you look closely, you'll see it only has 2 vertical semicircular canals, one anterior and one posterior. Now this 2-canal system, it was pretty good for some things. It could sense pitch, that's nodding your head up and down, and roll, which is tilting side to side. But it had a huge blind spot. It was completely deaf to yaw, that crucial side-to-side turning motion. Now, for a simple swimmer just trying to get by, that's not a big deal. But for a predator that needs to snap its jaws shut on fast-moving prey, that's a fatal flaw.
So, to make jaws truly effective, evolution had to solve this yaw problem. And the solution? It was a revolutionary upgrade to the inner ear.
And here it is. The solution was so elegant. A third semicircular canal, the horizontal one. This new piece of hardware became the shared, defining feature for every jawed vertebrate that came after. Its entire job was to detect rotation in that horizontal plane, finally giving predators the critical data they needed to aim their strike with deadly accuracy.
You know what's really incredible? Modern genetics has actually pinpointed the exact molecular architect behind this whole change. It's a single gene called OTX1. Now get this, when scientists knock out this one gene in lab animals, the horizontal canal just doesn't form. You end up with an inner ear that looks exactly like a jawless lamprey's. It's just a stunning example of how one tiny genetic switch can unlock a massive evolutionary leap forward. But, okay. Being a top predator isn't just about turning, right? It's also about lunging forward, stopping on a dime, sensing gravity. All of this required a parallel upgrade to the other sensors in the ear, the ones for linear motion, the otolith organs.
The original setup, which we still see in lampreys, was this single, large sensory patch called the macula communis. But the intense pressure to get higher fidelity, more precise motion sensing, drove this single patch to split apart and specialize into totally distinct organs.
And this split created a team of specialists. You got the utricle, which laid flat, making it the expert on horizontal movements and our sense of gravity. Then you have the saccule, which stood upright, specializing in vertical forces and vibration. And the lagina, well, it took on some other roles. This new division of labor meant the brain was getting much cleaner, much more precise information about all the linear forces acting on the body.
But just specializing the organs wasn't enough. Evolution added another brilliant tweak, the striola. This is a special zone where the sensory hair cells literally reverse their orientation. What this does is it creates this incredibly elegant push-pull system. So now instead of just sensing motion, the organ could actually tell the difference between forward and backward within the very same structure. This just sharpened the resolution of the signal going to the brain, providing a ridiculously precise picture of movement.
So after all that, what are the crucial points we should take away from this whole Gnathostome revolution? What does it all really mean for the vestibular system that we see in our clinics every single day?
Okay, let's pull it all together. First, the big one. The rise of predation was the main driver here. Jaws created the need for agility, and the vestibular system had to evolve in a big way to meet that demand. Second, the horizontal canal was the critical piece of new hardware for detecting yaw, and we even know the genetic switch, OTX1, that made it all happen.
And finally, the linear sensors got a massive upgrade, with the macula communis splitting into the utricle and saccule to give the brain much cleaner, higher fidelity data about linear forces and gravity, all supercharged by the evolution of the striola. We have mastered the water, but the land awaits. In video 3, Conquering Land, we explore the sensory crisis of the water-to-air transition and the birth of the neck.
Thank you for joining us for this deep dive into our vestibular past. To explore more topics like this one on dizziness, vertigo, and imbalance, and to get fantastic clinician and patient resource materials, please visit AustralianDizzinessClinics.com. And hey, while you're at it, please subscribe and leave a rating. We'd really appreciate it.